test. Okay. 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 Yep. So confirm now that stream is working. Yeah. Kind of froze, but was working a moment ago. So try this again. See if it works this time. So basically during the course of the past week or so, actually starting last weekend, but shortly after my last attempt to stream, I discovered that the Hexen source had been released as GPL, which is kind of useful. So I went and I ported that to BJX2. So that's what I have now, but it's being still pretty finicky as of yet, and I haven't actually really gone and optimized it or anything, so it's pretty slow. Along with, general chaos going on, but yeah. So actually, the crash in the second demo, I think, yeah, that happens in emulation as well. So while monitor's gone and got the wrong resolution, I'm going to see if I can get up and poke it without disturbing my epic wire mess. Okay, yeah, that's a little better. So I have in effect confirmed that, well, the epic slowness of Doom and Quake is at least not due to the use of 8-bit index color. Well, actually, to the use of 16-bit not index color. But yeah, because hex in here is using index color, and it is, you know, general appears to be at the moment pulling off frame rates actually worse than Quake does, so it's kind of yeah, so it's kind of, you know, pretty laggy. I'm not sure if other people can see, or, well, not assumption that anyone actually watches this, but if what I'm doing can actually be seen. But as it happens to be still daylight outside, which isn't great for being able to actually see stuff on this monitor, but looks like the webcam can still see it. See if I can make this a little bigger. So what's going on in this, yeah, laggy, blurry mess is, as noted, curious. There's lava there. Somehow I just, or I didn't notice that there's this lava in this map, and it actually doesn't really make any sense for there to be lava in this map, because, you know, this is one of those things that's generally easier to control under, scenarios where um, one can see what exactly it is they're doing, and and when it's not super laggy, which it kind of is right now. Yeah, as for the port, yeah, it's still using index color for now. I've yet to decide whether I'm going to leave it as index color or whether I'm going to rewrite it to use packed YUV or index or like high color. I could go either one. Actually, half thinking I might, if I do rewrite it, I might actually go high color this time because I'm not actually using color cell, and that's the main thing at the moment, which could justify the use of YUV. But yeah. Maybe I'll try going to the next map, because not a whole lot going on in this first map. What? Hold on, doing something right now. And it is frozen. Perhaps not too much of a surprise, but let this run and check on or go and check about maybe doing something. Okay, back. So, Doom is still doing its Doom thing. So what was thinking or going on? I forget. Yeah. Um, Doom at least works. Hexen still needs, well, at least some level of optimization and debugging because as it is, well, not exactly what could be called usable. Yeah, confirming that it wasn't the use of high color that was a problem, but actually, well, actually, I've not really identified the why performance is so bad exactly. I do know it's a bit better if it's, yeah, a bit better if it's if stuff is written in assembly than in C, but that is, possibly, yeah, not too much of a surprise. Uh, um, Best guess I have right at the moment is that, the pretty terrible performance is quite likely, well, beyond just the expected hardware limitations, um, possibly due to my not exactly all that great C compiler. As in profiling Doom and stuff, it's currently actually only spending about 12% of its execution time in the renderer functions, namely the stuff that I rewrote in assembler, but that remaining like 88% or so of the execution time is actually, most of the rest of the engine. So you have all this fun stuff going on, like yeah, you have all this fun stuff going on, like clock ticks and whatever else. And clock ticks and game logic and water wad lump lookups and all this other fun stuff that like people or the original versions of Doom seem to not bother trying to optimize, but in my case, like a lot of that stuff is currently actually being a majority of the execution time in Doom. Because, once the renderer was rewritten in assembler, then there's not that much, or yeah, then it's, you know, enough faster to where it's not really spending all that much time in it. Also, I'm just sort of casually messing around at this point, not actually trying to either move forward or recreate that bug on the next map, since, like, I think that bug has gone away now at least, so. And yeah, since that bug on the next map isn't really showing up, and there's not quite so much need to sit around going through little rituals trying to recreate it. But on that thought, like, you know, probably don't even really need to be messing around in this episode. I can go to a different episode and mess around there. Why not? The episode 4 maps in Ultimate Doom are basically just straight up absurd. But yeah. Switching it to low detail because I want better frame rates. And not exactly like I can see this stuff in. But yeah. First map of episode 4. We already got these guys. Which is, you know, and this is on the easy difficulty. That's like, so we got those guys on, like, the first map on the easiest difficulty in this episode. As you know, that part's just kind of absurd of this episode, but maybe if we wander around, we get to see some of the other stuff that's absurd with these maps. I don't think it's this map, I think it's the next one where you get to see we'll see some things. See some things like, check this crap out, a cyber demon on the second map. The question being, okay, why does it make sense for there to be a cyber demon here? Probably because they're all like, well, you know what? These maps aren't absurd enough. I'm gonna have a cyber demon. Oh, to be fair, I think there was like, BFG hanging around here somewhere as well, but yeah. Well, anyways. Probably obvious enough. So yeah, the general sentiment is, yeah, the CPU core, it does its thing, and it runs hexen. And I'm going to switch it off for now because, well, probably be demoed slightly better at a faster speed. Oh yeah. Do I want 150? I think I'll go 200. Because actual FPGA can't go this fast, but emulator, so why not? And people can see what it looks like if it's, not super laggy. You can actually see. So yeah, the hmm. Try this again. As noted, I've not exactly debugged this yet, and Hexen has shaken up. Okay, so no options menu this time. It worked before though. As can be inferred, a lot of the bugginess with this isn't actually due to the like CPU emulate, or actually the FPGA version, but actually it's pretty buggy in this form as well. But it does go faster, so it has that much going for it. Yeah. It can be noted that the actual code I got for Hexen when I initially started debugging it, or started trying to get it working, it's not exactly 64-bit clean, so had to spend a while like making making it where it wasn't like, you know, casting pointers to over to int or over to int and similar, and then casting back to pointers, because that kind of doesn't really work very well when you're dealing with 64-bit stuff. Breaking windows with the powers of cold. Is this dude is Mr. Freeze right now? Got these guys already. This guy. Interestingly enough, this particle effect is actually working on the BJX2 port, but isn't working on my Windows 64-bit port. Because yeah, in the Win64 port, they're just sort of, all the particles are just sort of forming in a straight line and then falling straight to the ground in a straight line, and that kind of doesn't look right. It's better when they're randomized, but haven't figured out what's going on there yet. Yeah. There seem to be, you know, behavioral differences between the, the BJX2 version and the Win64 version. So, not figure that out. I'm going to see if this is going to work. I think, yeah, this did work previously. Yeah, it did work previously, but I'll see if it works now. So, as some people might have ventured to guess, some of the bugs that exist on the CPU core or on the FPGA also still exist on the emulated version. But it's not a, yeah. Kinda still needs some debugging. Not sure how much is due to the code and how much is due to the, or due to C compiler bugs, but, did fix, some amount of C compiler bugs in the process of trying to get this to work as well, but, yeah. Now, on to the Windows version. So, I will... Yeah, it breaks in a straight line, which is not what it's supposed to do. Will menus work? I will see. Hit a debug or breakpoint there. Somehow I don't think that worked. Okay, so sound volume doesn't work, but yeah. Not sure about anyone else, but that was, you know, a little bit louder than intended. So So to do is, well, maybe figure out why they're breaking in a straight line on Windows 64, but yeah. The Win64 port is not really my intended main port here. But, you know. Also, yeah, another bug is, for whatever reason, background noises tend to be much louder than they should be. But then again, um, I did just sort of casually copy paste all the sound code from Doom in this case and hacked it to be able to work with Hexen, because in the form I got this code off the internet, it was basically lacking, well, most of the stuff. Sound code was they kind of ripped that part out. I guess because the version that was released was actually the DOS version, and so you had some stuff that was related to basically trying to make it work on an IBM PC on Wacom, but other than that, it was, yeah, I guess, a DOS version, and it was using a proprietary sound library, which they didn't include that, so they just sort of casually ripped that part out and released a partial release. In my case, I previously ported Doom over to Win64 and sort of copy pasted a lot of that code to make this port. Some amount of it didn't exactly fit correctly with the Hexen code, but I filled in the rest of stubs. So yeah, stubs and some amount of make it work code. Yeah, the result is, yeah. Yeah, the end result is I do now technically at least have a functioning Windows 64 port of Hexen. Let me check something. Yeah, I think in the past, like, normally if you fell down there, it kind of, it was kind of insta-death. Like, even with cheat codes and stuff, they still, caused it to cause insta-death if you fell to the bottom of that trench. pathway work? Yeah, it does technically at least work if one isn't no clipping through it. Yeah.
My servants can smell your blood, human.
Yeah, this here is technically the second hub world, but yeah. Yeah, stuff is at least slightly less crash prone um in this version, but still not exactly debugged. Also, this version can't exit via the menu because, yeah, that's still kind of a stub at the moment. So, and of course, yeah, you can tell that this is basically froze, like it did in the, or yeah, it froze in the PGA version as well. So, see what's doing. So, at least when it froze, 73% was going into the, looks like the end of the CLC function there. And, some drawing. More drawing. Okay, given that we still see these things here, that means that, it was at least probably redrawing the screen. I'll see what if I can figure out what is going on with, or that this stuff might have just been from before it froze. So, what can I figure out? Yeah, maybe it somehow got stuck in an infinite loop, like right there. Curious place to get stuck at. Let's see what the backtrace seems to say about it. Okay, so yes, it would appear so. So the link register got a value of 3.8, and that's where we're at. So yeah, it's just goes through that. It's the return thing. The link register takes it right back here, and so it loops. Does actually match with the output I was seeing on the 7-segment display. So yeah, emulator and FPGA version agree. And that means it's not a bug in my Verilog, which is probably good. And of course, does mean, yeah, my stuff is pretty buggy. Or pretty buggy still. Yeah, as far as, yeah, new developments, I had considered, trying to work more on, work more on task kern and similar. See if I can make it look kind of a little bit more like a real OS. Status there is, maybe work on the new P loader and task scheduling and similar. See if I can make all that fun work. Currently, well, that fun isn't complete yet. So my half-finished P loader, and straight up stub there, but not really finished yet, because, well, I intended to work on it, but I got distracted with other stuff. So what the new shinier P loader would do would be, well, it would first off be able to load multiple images at once, and it would be able to load images that are dynamically linked. The current existing loader, it only supports statically linked programs, which is kind of limiting, and it doesn't allow more than a single program to be loaded, which is not super useful. Also, a scheduler would be nice as well. As for whether or not I'll have preemptive scheduling, I've still not fully decided on that. I could have preemptive scheduling, but only if it exceeds a fairly long delay, like say 25 milliseconds or something, without a sleep, unless the process is declared as real time, in which case it'll probably assume round robin only, which means if the program gets stuck in an infinite loop, it kind of will cause the thing to freeze, but that's not too much worse than how stuff is generally working on it already. But yeah, because at the moment stuff, it tends to just crash and require hard resetting all the time anyway, so not too much of a difference. Yeah, would mostly want that for real time, or for real time stuff. But yeah, preemptive scheduling probably does make sense, or at least for non-real time processes, which would probably be the default. Have to think of the specifics of how you'd tell it to load a program as real time versus non-real time, but yeah. Unless maybe there's a system call for hey, this current process needs to be a real time, which I could probably do. In any case, task kern is probably going to remain as a single big address space with all the programs loaded into it and stuff. Yeah, so the idea will be, everything will be loaded into a single big address space with yeah, with more or less multiple, um, or yeah, with each instance having its own copies of the data and BSS sections. These, of course, um, use the whole PBO ABI mechanism, which just sort of daisy chains them all together. So um, all the data and BSS sections from one from one process image will be all linked together, and it'll be possible to daisy chain from one to the other within that process, and all the other ones from a different process will be linked together in a similar way, just separate. Otherwise, yeah, there's not going to be that much isolation between processes. Apart from possibly in the future, I will probably use the whole UGID thing to provide some semblance of memory protection. As yeah, at this point, probably having an OS that's all like straight up DOS style with no memory protection is yeah, well, probably won't fly that well. People would at least want something going on to prevent one program from stomping on all the other programs, or one program from stomping or straight up stomping on kernel memory. But yeah, otherwise, yeah, in that sense, it will have more in common with something like DOS or Windows 3.0 or something than it will like a more modern OS. But in this case, yeah, I control the hardware, so I can make whatever I want work. Also have considered an idea for yeah, clearing out Notepad. I can pull it over. Yeah, I'd considered possibly an idea for an instruction for doing tagged pointer manipulation. So you'd have basically just having to remember what I was thinking. Oh, 10-bit immediate, and then so a load and compare tag instruction with a 10-bit immediate. Well, this inherently doesn't seem that notable. It'd be all like, well, what use can you do with a 10-bit immediate? That's way too big for dynamic type tags for pointers, and how do we know where it is and all that stuff. But I came up with a solution to that. So have a 10-bit immediate representing a tag, but it doesn't just represent a 10-bit tag. It actually represents all possible tags from 1 to 8 bits. So we'll say you have so 10-bit tag looks epic. So this is basically and this one is so basically, yeah, low bit and high bit. So That's great. So what? But you know, can be all like, and so now that shifts one bit over, and suddenly it addresses 2 bits, and we can tell these apart because you know, see, well, zero, it's all zeros here, and it's all zeros and a one here, so you can see where the one is, and it extends a little bit further. So if we put a bit here, take a bit here, change this to a 3, now we have pattern extends to 3 bits, and 4. Continuing on. So 6 bits. 7 bits. And 8 bits. So simple scheme can encode both the low and high bit pattern, or anywhere from a single bit up to 8 bits. Now if we use the Q bit, we can use the Q bit to select whether we want to apply it to the low 32 bits or the high 32 bits. So now we have access to, you know, a fair range of bits in the in a 64-bit value, so you can fiddle with, you know, the low few bits of a 32-bit tag pointer, or the high order bits of a 64-bit tag pointer, or of a 32-bit tag pointer, or whatever, or we can just use it for general bit manipulation. So that will all work. But yeah, the concept of this instruction is simple enough, and it might actually help enough to be useful with dynamically typed stuff, but still to be seen. Because I'm not entirely sure about cost, which is something. So, kind of what it looks like in Verilog thus far. Same basic pattern. It will just, follow this pattern and use it. It's split over 2 cases rather than, a single massive case. But, same basic idea. Just checks if the high order bits are 0, and we'll use the one for the low order one, or if it's non-zero, we'll use the high order one. Haven't yet written the logic for comparing the tag, but yeah. One could be like, well, how does that really help? It, it's a question of it might. So if you want to say add two tag numbers, what you can do is basically just that. So you add two numbers, you can do it like they are normal integer values, and of course, um, if they if like they're negative or something, bits would carry out and trash the tag. But then in this case, it'd be all like so. No, do it. So in this case, I'll say so in this case, yeah, this will actually, yeah. So in this case, it would just sort of set the high 2 bits to like 1 0 and achieve the technique of making sure that the bit pattern for tagged integers remains intact. Tag pointers would basically be something vaguely similar as well. Actually, we don't need special manipulation for tag pointers, but yeah, we might need to check it. So could be all like for our logic for say doing a binary add object like that thing, be all like basically be all like if either of these two are, well, not tagged integers, then it will branch to the label, and then we can be all like use this logic, add as a tag or add value, make sure it stays a tagged integer, and suddenly like, well, not perfect because you'd still need the big decision tree to actually get to the correct branch for doing the operation. It is at least a little bit less bit manipulation to actually get there. So conceivably dynamic types could be a little bit less terrible. Um, as for how quickly it could be able to handle tagging schemes based on NaN tagging or something, yeah, that wouldn't fit quite as well within this mechanism, probably, but yeah, could be viable. Could at least check the high order bits and be able to detect reasonably quickly if it's not a NaN. Like, well, we have a pattern that could conceivably be a NaN, and if not, yeah, we know it's not a NaN, so we can just fall back to treating it as a double or similar. And if it isn't, and if it could be a nan, then we can check a little bit more and be all, yeah, is it a nan? And if yes, then we can go through that branch. Mm-hmm. So, like, is it potentially a positive infinite or nan in these two cases? We can detect it. Won't detect it reliably because it could just be a rather large floating point number, but you can detect like that when you get to it. But in any case, the vast majority of normal floating point numbers will just fall through, and then we can be like, yeah. So now suddenly we can, just be all like, is it okay? Is it potentially a nan? And is this one potentially a nan? So we can go down here and, do whatever to do more checking or similar, or, be like, no, it's not a nan, so we'll just fall through to this branch and add, do a floating point add and return the result. Yeah. The burning question might be, well, how would you do this if you, well, didn't have this magic going on? So, otherwise, you might do something like this. This, um, if we consider that, like, we don't actually have the ability to do a compare against a full 12-bit immediate, so this would be, 2 instructions for the compare. for the one for the constant load and one for the compare probably. But we do have a 10-bit, so do that. Now it's down to single instruction. So 2 instructions, latency to get to here, instructions to get to here, and yeah. This is, of course, arguably the main thing against adding instructions for this specific thing, is if you can just be all like, yeah, do the same basic thing but with only a few more instructions, which kind of diminishes the gain of having a special instruction for dynamic type tag fiddling. At least if adding such an instruction isn't borderline free. But loading the tag bits is arguably a little bit more useful. At least, yeah, in that, you actually have to do a little bit more bit manipulation, like anding and oring, and stuff to actually be able to do the bit twiddly. So, so yeah, LDI tag is potentially more useful than the compare tag, but yeah. Because, yeah, how would you load the tag if you didn't, yeah, how'd you load it if you didn't have it? Oh. So, this can be done as a single instruction, and this, yeah, also can be done as a single instruction. So, 2 instructions to load this particular constant, or to load basically a 3 R3 followed by a bunch of F's constant. At least this is this would be the more space efficient option. Jumbo, you can, directly load the constant, but it will take more space. So, but yeah, what do you do with this? So so mask off the bits we don't care about. and then get it back to 4,000. Actually, this almost works, but you know, change it to R2, then it's, you know, properly in the return value. So it can be all like, yeah. So yeah. So yeah, single instruction. And 5 instructions. So yeah, that would probably constitute an advantage if you are doing this a lot. Which in a dynamic language, yeah, that's quite probably going to be happening a fair amount. So it might be justifiable. We'll of course still have the disadvantage that you have to go down different logic paths depending on the size of the type or type of the type, but you know. Otherwise, in other recent news, long double is now a 128-bit type. This is a minor change. Previously, long double was being interpreted as an alias to double, but yeah. But long double isn't really being used unnecessarily, and it actually makes sense to have long double as an alias for float 128 rather than an alias for double. So then you can be all like long double, and or you can type long double and technically have or still have standard C code but have 128-bit precision available. So yeah, of course that 128-bit precision would be notably slow. Yeah, chances are if you're using long double, you're not necessarily also wanting it to be fast at doing so, at least within reason. Yeah, double would at least still be a little bit faster. Yeah, some interruptions, but not sure if I have that much else new at the moment. Yeah, probably all for now.